Please note at the very beginning of our broadcast that this is an AI-generated analysis.
Indeed it is.
Imagine a React application so massive and interconnected that simply changing a user's visual theme from light mode to dark mode causes the entire browser window to, well, freeze for 3 agonizing seconds.
That is a critical structural failure.
It is. Today we are conducting a comprehensive analysis of the book Advanced React Patterns by Pedro Martins, which was published in February 2024, to ensure you never build that fragile application.
Our mission is to extract the crucial architectural patterns, state management solutions, and performance optimization techniques required for building highly scalable web applications.
Precisely. Whether you are an intermediate developer seeking to elevate your structural understanding, or a software architect tasked with standardizing practices across multiple engineering teams, this analysis will clarify the exact mechanisms of modern React development for you.
To prevent those cascading performance failures you just described, we must start at the microscopic level, the structural foundation of individual components.
Because before a developer can safely manage vast amounts of data, the architecture of the basic building blocks must be perfected.
Correct. The text begins by focusing heavily on decoupling core business logic from visual presentation. This decoupling is achieved through several advanced component patterns. The first pattern is render props.
And render props allow a component to encapsulate complex behaviors, correct?
They do. Behaviors such as tracking a user's mouse coordinates. You share that specific behavior by utilizing a property whose value is a rendering function.
I see. So the child component dictates how the data looks, while the parent strictly dictates how the data behaves.
It's exactly that mechanism. Another foundational technique is the use of higher-order components, or HOCs.
HOCs.
Yes. These are functions that take an existing component as an argument and return an entirely new, enhanced component. It is highly effective for injecting shared logic.
Like an authentication check.
Indeed. You can inject an authentication check across dozens of disparate screens without duplicating any code. Furthermore, the author details compound components,
which involves multiple discrete components working together in tandem, like a navigation tab and a content panel.
Precisely. They share an implicit state under the hood. This allows them to communicate and function as a single cohesive unit while remaining visually completely separate to the developer consuming them.
That structure leads us directly to the provider pattern, which solves the fundamental problem of passing data deeply through these component trees.
It is a critical solution.
To visualize the provider pattern, you can compare it to a high-powered radio tower broadcasting a signal across a city. Any tuned-in radio, which represents an individual React component in this analogy, can receive the broadcast directly.
That is a highly accurate comparison. The broadcast signal might be the application's visual theme or the current authentication state.
And this mechanism completely bypasses the need for physical wires connecting every single room from the tower down to the basement.
Because in React terms, those physical wires represent the tedious, error-prone process of prop drilling,
where properties are manually passed down through every single intermediary level, even if those levels do not actually need the data.
Correct. But, building upon that structural foundation, perfectly decoupled components remain entirely static without internal memory and lifecycle awareness.
Which introduces the complexity of component state, managed exclusively through hooks.
The text provides a rigorous exploration of functional memory. It traces the essential evolution from basic hooks like useState for simple data retention to useEffect for managing external side effects.
And with useEffect, the author emphasizes the absolute necessity of cleanup functions.
It is a non-negotiable necessity. Consider a scenario where a component subscribes to a live WebSocket data feed for financial trading.
If the user navigates away from that dashboard, and the component does not return a cleanup function to sever that specific connection,
the application will continue processing background data for a screen that no longer exists. This results in severe browser memory leaks and eventual crashes.
The analysis also covers useRef.
Yes, this hook maintains mutable data references that persist indefinitely across renders without ever triggering a new rendering cycle.
Which is essential for interacting directly with native document object model elements.
Precisely. Now, the distinction between rendering cycles brings us to a highly specialized hook, useLayoutEffect.
While a standard useEffect allows the browser to paint the screen visually before executing its background logic, useLayoutEffect operates synchronously.
It forces the browser to Well, to halt the visual painting process entirely until all internal calculations and document object model mutations are completely finished.
This prevents that jarring visual flickering that occurs when an interface element needs to measure its own physical dimensions before deciding where to position itself.
Correct. And for deeply nested, highly complex state logic that requires multiple subvalues to change simultaneously, the author strictly recommends transitioning away from use state.
Toward use reducer.
Indeed. Use reducer provides highly predictable state transitions by defining explicit, strictly formatted actions, heavily mirroring external state machines.
Once components are efficiently structured and possess sophisticated internal memory, the immediate subsequent challenge you face is sharing that dynamic data between them,
Without recreating the tangled web of properties we previously avoided.
which introduces the core state management dilemma. The built-in context API is evaluated using a global theme switcher as the primary use case.
However, relying solely on context introduces significant performance pitfalls at scale.
Because by default, when a single context value changes, every single component subscribing to that context will forcibly re-render.
Regardless of whether it actually utilizes the specific variable that was altered.
To mitigate this catastrophic performance degradation, the text mandates combining context with use reducer to centralize the logic,
As well as utilizing context selectors to carefully isolate and subscribe to specific data fragments.
and employing lazy initialization to delay expensive memory calculations until the data is genuinely required.
That is correct.
This analysis of state management raises a critical question for you regarding exact thresholds. If we can combine the built-in context API with use reducer to effectively construct a localized global state system, at what specific threshold of application complexity must a development team truly accept the heavy boilerplate overhead of an external library?
Like Redux or MobX.
Yes. Are these external libraries mandated by the sheer volume of data stored in the browser? Or are they dictated by the frequency and velocity of the state updates?
The author specifies that the threshold is dictated primarily by the velocity of the state updates and the complexity of the asynchronous side effects.
So the context API is well suited for low-frequency updates.
Indeed, such as a user modifying a local erasure preference or updating an avatar image.
But if your application processes high-frequency updates, such as a live collaborative document editor,
The context API simply cannot filter the rendering cycles efficiently enough. It will trigger an unacceptable volume of unnecessary component recalculations.
at that high-velocity threshold, you must adopt external solutions.
Redux provides a predictable, strictly unidirectional state container. It enforces rigid rules requiring actions and reducers.
And it explicitly demands middleware, like Redux Thunk, to manage the lifecycle of asynchronous operations.
Like pausing the application while fetching data from a remote server. In direct contrast to Redux, the text details MobX.
Which utilizes functional reactive programming.
Correct. It relies on a proxy-based observer pattern to track state changes automatically. This allows developers to write significantly less boilerplate code than Redux.
While providing fine-grained reactive updates that surgically re-render only the exact microscopic components connected to the altered data.
Efficient, surgically precise state management logically dictates a focus on overall application performance.
Because a flawlessly managed data state is entirely useless to you if the actual user interface remains sluggish, visually unresponsive, or takes 10 seconds to initially load.
Therefore, we must review the profiling and optimization techniques required for enterprise applications.
The text details the precise usage of React.memo for functional components.
This specialized tool prevents unnecessary re-renders by executing a shallow comparison of incoming properties. If the new properties match the previous properties exactly,
The component skips its internal rendering process entirely, saving valuable processor cycles.
the analysis also explores code splitting through React.lazy. Instead of forcing the user to download the entire application architecture in one massive file, React.lazy physically splits the compiled JavaScript bundle.
Allowing the browser to request and load specific administrative panels or complex charting libraries only at the exact moment the user attempts to access them.
To maintain a highly responsive user interface during complex operations, the text advocates for utilizing web workers.
JavaScript is inherently single-threaded, meaning a heavy calculation will freeze all visual interactions.
Web workers allow developers to offload massive central processing unit-intensive tasks to a completely separate background thread.
Like parsing a massive spreadsheet document.
Precisely, ensuring the visual interface remains completely fluid.
The text also details the mandatory optimization of visual assets, recommending modern image formats like WebP lazy loading non-critical media, and preemptively preloading essential typography fonts.
Expanding on performance abstraction, custom hooks are presented as the ultimate mechanism for isolating complex side effects.
Developers can construct a use WebSocket hook to completely encapsulate the lifecycle of real-time data connections.
Or a use interval hook to manage the delicate timings of polling a server.
This architectural abstraction keeps the main component logic exceptionally clean.
Now, when managing these complex network side effects and unpredictable user interactions, the text introduces the critical concepts of debouncing and throttling event handlers.
You can understand the exact mechanism of debouncing by visualizing an elevator door in a busy lobby. The mechanical door waits until the final person has entered the cabin, and then waits a specific number of seconds before it finally attempts to close.
And if another person approaches and triggers the sensor, the timer resets completely.
It will not close until a sustained period of inactivity occurs. In a complex React application, debouncing is typically applied to user input, such as a live search bar.
If a user takes 10 characters rapidly, debouncing literally prevents the application from accidentally launching 10 simultaneous network requests to your database.
It essentially prevents a user from accidentally launching a distributed denial-of-service attack on your own servers through rapid, continuous inputs.
With optimized individual components and efficient state management established, this comprehensive analysis must now zoom out to the macro architectural level.
We must evaluate how development teams organize thousands of these components into a massive, scalable codebase.
The text summarizes architectural best practices, advocating for a fundamental shift toward feature-based folder structures.
Historically, developers grouped all styles in one directory, all network requests in another, and visual components in a third.
The modern approach groups everything related to a specific feature, such as the user billing dashboard, into one highly cohesive directory.
The author formally introduces domain-driven design into the React ecosystem, structuring the application around bounded contexts.
For extremely large organizations, the text details the concept of micro-frontends. This allows different engineering teams to build, test, and deploy completely separate segments of the user interface entirely independently,
utilizing continuous integration pipelines to guarantee automated testing. However, I must challenge the strict recommendation for feature-based folder organization.
On what grounds?
When you adopt domain-driven design in a React frontend, isolating your code into highly specific feature-based folders, how does a team prevent these folders from becoming impenetrable silos? It seems highly probable that teams will accidentally duplicate shared user interface logic.
Resulting in 4 different definitions of a standard submit button.
Precisely.
The risk of isolated silos generating duplicated code is a significant, heavily documented architectural failure point. The author acknowledges this vulnerability.
And how is it mitigated?
By dictating the strict implementation of a centrally governed shared components directory. While specific business logic remains isolated within feature folders, any visual element utilized across multiple domains must be mathematically abstracted into a central library.
I see. Creating and maintaining this centralized design system requires strict governance and cross-team consensus.
It is an absolute architectural prerequisite to achieve an infinitely scalable structure.
This meticulously organized architecture is especially critical when dealing with the most volatile aspect of any application, raw user input.
The text transitions to advanced patterns for constructing complex, multi-layered forms.
Forms require meticulous high-velocity state management and rigorous validation rules. The author details building custom use form hooks to encapsulate the chaotic input handling.
For multi-step paginated wizards, the recommendation is to manage the complex linear state transitions utilizing reducers.
The text also evaluates the integration of powerful third-party libraries, specifically Formic and React Hook Form.
React Hook Form is highlighted for its ability to register form inputs directly into the document object model,
bypassing the React rendering cycle entirely during keystrokes.
This handles complex cross-field validation without causing severe rendering performance degradation.
As the architectural foundation scales, the application inherently requires strict mathematical contracts to prevent critical runtime errors.
Relying on human developers to perfectly remember the shape of every data object is an engineering failure. This introduces the absolute necessity of TypeScript,
which provides rigorous compile-time type checking. This mechanism guarantees that structural errors are caught instantly by the code editor long before the application is compiled.
The text details how to explicitly type the incoming properties for all components, establishing an unbreakable contract.
Furthermore, it demonstrates how to strongly type the context API by utilizing defined interfaces.
And it explains the specific syntax required to accurately assign types to React event handlers, ensuring complete memory safety for mouse clicks and keyboard inputs.
To conceptualize the sheer value of TypeScript, you can liken it to a highly advanced, physics-aware structural building inspector reviewing a blueprint.
A standard spell checker merely confirms if a word exists. TypeScript understands the physical limitations of your architecture.
It will not physically construct the application for you. However, it will immediately halt the entire building process if you attempt to use a text string where a numerical weight-bearing metric is explicitly required.
It mathematically enforces structural integrity. Extending that concept, the text explores the utilization of TypeScript utility types to manipulate these strict contracts dynamically.
Specifically, the partial, read-only, and record utilities.
These advanced tools allow developers to take an existing, rigid data interface and transform it mathematically to build highly flexible, yet completely secure component properties.
For example, if you have a massive user profile interface requiring 50 properties, the partial utility allows a specific subcomponent to safely accept a subset of those properties without triggering a compiler error.
This is exceptionally effective when constructing update functions that only modify localized pieces of a larger global data object.
A perfectly typed, structurally optimized application must ultimately be connected to external data sources and successfully delivered to the end user.
Which brings us to the final mile of our detailed technical review, encompassing routing, network communication, and deployment strategies.
The analysis evaluates nested route structures, highly protected routes requiring cryptographic authentication, and dynamic route segmentation using the React Router library.
A major paradigm shift detailed in the text is the modern abstraction of server state. Instead of manually pushing fetched server data into a global Redux store, the author strongly recommends utilizing specialized asynchronous libraries.
Like SWR and React Query.
Indeed, these specialized tools automatically handle the complex lifecycle of network requests, managing background caching, and automatic retries upon failure.
To ensure the user interface always displays the most current database information. The text also covers leveraging the React Suspense API to declaratively display fluid loading states while this data is retrieved.
The analysis transitions directly from data retrieval to final deployment execution. It details the absolute necessity of build optimization. This includes a process known as tree shaking.
To visualize this, imagine your codebase as a literal, physical tree. When the production build process shakes this tree, any dead, lifeless leaves, which represent unused JavaScript functions, physically fall off.
This automated pruning guarantees you only transmit the living, strictly essential code branches to the user's browser.
The text also covers secure environment variable management, emphasizing that cryptographic server keys must never be accidentally bundled to the client interface.
Crucially, the author heavily contrasts static site generation with server-side rendering.
Static site generation compiles the final HTML pages exactly once during the initial build process, creating highly optimized files that load instantly.
Conversely, server-side rendering compiles the HTML dynamically on the remote server every single time a unique user makes a request.
Which requires more processing power, but is strictly required for highly personalized, constantly updating content. The text mentions deployment platforms like Vercel and AWS Amplify that support these advanced rendering techniques natively.
They do.
Looking at the rigid, historical binary presented between static site generation and server-side rendering, we must actively question if this strict distinction is becoming functionally obsolete.
In what way?
With the rapid advent of hybrid architectural approaches like incremental static regeneration, where pages are initially built statically for immediate speed, but are then quietly regenerated in the background upon subsequent user requests. Are we moving toward a future where choosing strictly between static and server-rendered architecture is an outdated concept?
The author addresses this precise evolution. Incremental static regeneration effectively obliterates the old binary, blending the instant delivery performance of a static site with the real-time data accuracy of active server rendering.
So developers now deploy hybrid rendering architectures, meticulously applying the exact compilation strategy on a microscopic page-by-page basis.
Correct. This continuous evolution leads perfectly into the final thoughts of the book, which focuses entirely on the architectural future of React. The text heavily analyzes the upcoming impact of React server components in concurrent mode.
With server components, the actual execution of rendering logic will increasingly be split horizontally.
You will execute heavy database queries securely and directly within your React components residing on the server, serializing the data and transmitting only the compiled visual user interface to the browser.
Significantly reducing the amount of JavaScript the client must process.
That structural shift suggests a fundamental reality. The traditional definition of a front-end developer will change in the coming years.
To build scalable, performant React applications in the future, you will be required to encompass traditional back-end optimization skills, bridging the historical gap between direct database query performance and fluid user interface design.
The imminent transition towards server components mathematically ensures that our foundational understanding of React architecture must continually and rigorously adapt.
We strongly recommend that you read the actual book, Advanced React Patterns, by Pedro Martins.
Engaging directly with the complete text will allow you to see all the complex code examples firsthand and mathematically implement these scalable architectures in your own enterprise projects.
Thank you for joining us for this comprehensive analysis. To all the friends of the show listening, we highly encourage you to subscribe to the broadcast for our future detailed technical reviews.
We wish you a great day.